The software package we will use in this class for performing our numerical simulation is something called Simulink. Simulink is an add-on to the program MATLAB, which we've already introduced in this class. Simulink represents models as block diagrams, and an underlying solver, like Euler's method, which we introduced, is used to approximate the values of the variables. Within Simulink, you can choose the solution method, for example, a higher order solver than Euler's method, and you can also specify the time step that the simulation uses. Simulink includes a large library of different mathematical functions, including many types of nonlinearities. At this point, we will introduce briefly how to model different types of mathematical models within Simulink. It is likely you've had some introduction to Simulink in previous classes, but if you haven't, that's okay. I won't assume any prior knowledge, and if you have additional questions, please feel free to ask me outside of class. So this is a differential equation, a second order differential equation with a forcing input of u, and it's modeled by this Simulink block diagram. And so the correlation between these two is as follows. So in this case, u is modeled as a step input, and so there's a block within Simulink for a step input, and that signal u is multiplied by a constant b, where this is also a standard block within Simulink. So that's u times b. Rearranging this differential equation, we can see that y double dot is equal to minus a1 times y dot minus a2 times y plus b times u. So this signal here is the plus b times u. It turns out that this signal right here is going to be y dot, and this signal here is going to be y. This signal y, when we branch it off, the signal remains y. We put it through this gain A2, which multiplies the input signal. And so this signal is A2 times y. Similarly, when we branch off here, this signal is y dot. Multiply it by a gain, and so this signal is A1 times y dot. This is a common element of a block diagram called a summing junction, which we introduced. The signal b times u is on a positive input, while these other two signals are on a negative input. So what this signal coming out of the summing junction is it's negative a1 times y dot minus a2 times y plus u times b. So in essence, this signal is equal to this, which we can see is equal to y double dot, the second derivative of y with respect to time. This block is an integrator, and if you think back to our properties of the Laplace transform, the Laplace transform of integration in the time domain becomes division by s in the Laplace domain. And so that's exactly what this represents. This represents division by s, and so the integral of y double dot is y dot, and if we integrate it again, we get y. This may take a little practice, but hopefully you get a sense of how to translate a differential equation into a Simulink block diagram. One of the nice things about differential equations is that you can include the initial conditions in the model. The way that you do that with Simulink is if you double-click on these integrator blocks, you can set the initial condition. So for example, the initial value of y is set in this block, and the initial value of y dot is set in this block. Furthermore, with these differential equation models, you can include nonlinearities. So there's many blocks within the Simulink library where you could, for example, square y dot, or you could, for example, take the sine or cosine of y and add it simply into your model. An alternative to a differential equation model, if you recall, is a transfer function model. And the way that we find a transfer function from the differential equation is we follow a few steps. First, we identify what the inputs and the outputs are. In this case, u is our input and y is our output. Then we take the Laplace transform of the differential equation and we assume zero initial conditions. So we take the Laplace transform of this, and then we rearrange it into the form of output over input, y of s divided by u of s. And if we do that, this is the resulting transfer function that we get. And so there's a block within Simulink that represents transfer functions. And there are many nice things about transfer functions, one of them being that they're algebraic. So no derivatives, no integrals. It's only multiplication and division by s. They're nice for combining complicated systems, systems in series, for example. Unless, of course, you have loading in your system, then you need to be careful, as we talked about when we were modeling circuits. We also need to be aware of the fact that this transfer function doesn't capture the initial conditions of the system. When we found the transfer function, we assumed that the initial conditions were zero. Furthermore, we cannot represent nonlinearities. So the Laplace transform of a nonlinear function of y can't be performed. So this gives you some ideas of sort of when you may want to choose a differential equation model and when you may want to choose a Laplace transform or transfer function model. So now I will go ahead and open up Simulink and step through a very simple example of how to model a differential equation. So hypothetically, let's say that we have a first order differential equation of the form x dot plus 5x equal to u. If we were to solve this differential equation, we would have a homogeneous portion and a particular portion. Looking at the left-hand side, the characteristic equation of this differential equation would be lambda plus 5. Therefore, it has a root of the characteristic equation of negative 5. The negative 5, since it's real, it indicates the rate of decay. So we would expect that the solution x of t would decay like e to the minus 5t. Since there's no imaginary portion to the root, we would expect there to be no oscillation, where the imaginary part tells you the frequency of oscillation. So this is the homogeneous solution. We would also expect a particular solution, which would have a similar form to the forcing function u. If we assume that we have a constant input or a step input, then our particular solution would also have the form of a constant or a step. So if we were to simulate this differential equation, we would expect the response to look something like this. If we rearrange this, we could see that x dot is equal to negative 5x plus u. So we would imagine that we may have some block for u in our Simulink diagram. It'll go into a summing junction where u is going to be on the positive signal, and then we're going to subtract 5x. So we'll have a negative input. And we'll have some gain of 5 multiplying x. On this signal we have a positive u. On this signal we subtract 5 times x. The combination of those two is x dot. To get from x dot back to x, we need to integrate. So we'll have an integrator block, 1 over s, where the output of that is x. We branch that off to get that feedback signal there. And then we'll have this is our output, x. So I'm going to open up Simulink and we're going to recreate this and verify that the response has a form that we expect.